Hi everybody, I'm Francesco Soberano, and I'm going to present you our paper, From Philosophy to Interfaces, an explanatory method and a tool inspired by Achinstein's theory of explanations. Nowadays, algorithmic decision-making is changing industry. This is why people and countries began to be concerned about the impact that may have on everyone's lives. This is one of the reasons that gave birth to the so-called right to explanation, recently introduced in the EU legislation, and further explored by the High-Level Expert Group on Artificial Intelligence, established in 2018 by the EU Commission. Some of the given guidelines point to the need for user centrality in explanations. The fact that explanations are better conceived when they are pragmatic is also shared by all the most recent philosophical theories of explanation. Explanation in philosophy has been conceived within the following 5 traditions: causal realism, constructive empiricism, ordinary language philosophy, cognitive science and naturalism, and scientific realism. The first one is not pragmatic, the others are pragmatic. Apparently, a lot of literature on user-centered explainable AI is now steering towards the interpretation of explanations given by cognitive science. But in our paper, we propose a new approach to explanations in AI that is mainly inspired by ordinary language philosophy. Achinstein's model is probably the most prominent example of theory of explanations within the scope of ordinary language philosophy. According to this model, explaining is an illocutionary act coming from a clear intention of producing new understandings in an explanee by providing a correct, content-giving answer to a question. But what is illocution precisely? Our hypothesis is that illocution in explanations is equivalent to the act of pertinently answering to archetypal questions, such as why, what for, how, when, and so on. In fact, explaining is not just answering a given question in a punctual way, that would be simply answering, but it is also answering all the other implicit questions defined by the explanee's background knowledge, the objectives of the explanatory process, and the given context. In other terms, the more archetypal answers about the explanandum's aspects are covered by the act of explaining, the more likely the resulting explanation is going to meet the explanee's objectives. So, how can we measure the pertinence of an answer? The likelihood of pertinence to an answer can be quantitatively estimated with strong enough statistical evidence. For example, collected in deep language models as suggested by existing literature. But we are defining pertinence by means of statistical tools. Where is user centrality in this? A statistical definition of pertinence doesn't preclude a pragmatic iterative explanatory process that is locally non-pragmatic but globally pragmatic. In other words, an explainance at step T is non-pragmatically built by organizing knowledge according to a statistical pertinence, but the sequence of explainance is pragmatically chosen by the users. So we can design an explanatory process as an iterative process where user centrality is in the way answers are visited, explored, expanded, and eventually asked. So far, we discussed about theory. How can we build this iterative process in practice? To do so, we need an algorithm for the extraction and organization of explanatory spaces, or ES in brief, out of explainable documents. An ES is defined as the set of all possible explanations on an explainable explanandum, reachable by a user through an explanatory process, starting from an initial explainance via a predefined set of actions. Therefore, an ES is a graph of interconnected bits of explanation that are about different aspects of the explanandum. To every aspect is associated an information cluster explaining that aspect. An explanatory process over an explanatory space can be defined by the choice of appropriate heuristics for visiting and organizing the space. To this end, we identified the R's heuristics that are abstraction, relevance, and simplicity. Abstraction is for selecting and organizing the different aspects of the explanandum. For instance, the core aspects to explain might be the different concepts or entities mentioned in the explanandum. Relevance is for organizing the information about the aspects according to the archetypal questions. Simplicity is for filtering or grouping the edges of the graph. For instance, some pieces of information can be hidden because redundant, or some others may be grouped together to simplify the visualization. In order to implement these ARS heuristics, we created a pipeline for extracting a knowledge graph of aspects out of natural language documents, building information clusters for every aspect according to the identified archetypal questions, presenting information clusters through a simplified hierarchy of expandable summaries. We put this pipeline at work. If our hypothesis is correct, through the identification of a minimal set of archetypal questions, it is possible to obtain a generator of explanations that is good enough to significantly ease the acquisition of knowledge, thus resulting in a user-centered explanatory tool that is more effective than its non-pragmatic counterpart on the same explanation, of course. To verify this hypothesis, we designed a user study on a baseline credit approval system. The baseline credit approval system we are considering has been designed by IBM, and it consists in explainable AI used to generate a static explanation about the system's decision. This explanation is meant to explain to a customer what to change in order to get a loan application accepted. On the left, you may see a screenshot of such explanation. For the sake of the experiment, we created an interactive version of that baseline that is using our pipeline for generating explanatory overviews of the explanandum's aspects. This interactive version is obtained by means of a JavaScript module that automatically annotates the static explanations by using the extracted knowledge graph. The documentation we used for building the knowledge graph was taken from roughly 60 online web pages. As a result, the user can interactively explore the explanatory space by clicking on annotations, opening an overview containing further annotations. As we can see on the image on the left, information is organized according to the ARS heuristics. Aspects are explained through expandable archetypal answers, summarizing more punctual information. For the user study, we recruited more than 100 different participants. The first half of the participants tested the baseline system, while the second half tested our extension. Participants were invited to answer two sets of questions, a SUS questionnaire and some domain-specific questions. The set of domain-specific questions was used to measure the effectiveness and efficiency of the explanatory tools. Importantly, more than 70% of these questions were designed so that the correct answers were not immediately available in the initial explanans, forcing the users to visit multiple nodes of the explanatory space. The participants of Group 1 were explicitly allowed to search the web for the correct answers that were available online on the websites used for the extraction of the knowledge graph. We chose to not make assumptions on the distribution of the collected data. This choice excluded a lot of statistical tests. So we performed a few one-sided Mann-Whitney U tests. The results showed that effectiveness, that is the number of correct answers, was significantly greater than the baseline with a p-value lower than 0.05. There was not enough statistical evidence for claiming anything of satisfaction or efficiency. Conclusions. We proposed an original and generic paradigmatic explanatory AI inspired by Achinstein's illocutionary theory of explanations, where most of literature usually prefers to focus on cognitive science. We also proposed a way to concretely implement illocution as the act of pertinently answering archetypal questions. We tested our theory inventing a new pipeline of AI algorithms and running a user study on a realistic credit approval system, showing a statistically significant improvement in effectiveness over the non-paradigmatic explanatory AI provided by IBM. Thank you for your attention.